Here's an example of a two-dimensional electrostatic force question where we employ the principle of superposition and some basic trig. You can see the problem description in a little diagram. We have a positive and a negative charge shown on a horizontal axis, and then a point P shown on the bisector line to that axis, and the coordinates of each of the points is marked on there. And the question is what the magnitude and direction of the force would be if an electron were placed at point P. So I'm going to indicate that here, as we often do for a negative charge. We'll put a little blue mark there, and then indicate 1.6 times 10 to the minus 19 coulombs. That's known as the fundamental charge. And now we can start talking about the direction of a force on there. Because the force due to the negative charge will be repulsive, that means we can draw a force arrow up and away from the negative charge, but a force due to a positive charge will be attractive. And here's where we can use some symmetry here. Notice that the electron is on the bisector, which means it's equidistant from both charges, and so we will have an identical vector just down and to the right instead of up and to the right. So what we'll see here is when we use the principle of superposition and add those two together, we'll get what we refer to as canceling components and summing components. I'm going to show the canceling components in red. In this case, this one has an upward component, and this one has an identical downward component. And we're not going to consider those because in the vector world, those completely cancel each other out. What we do need to consider is the summing components, which are both rightward. And so if we could just find out how big one of those is, and we just need to double it, and we'll have the force due to both of them. So now we're going to get into the math a little bit. We're going to use Coulomb's law, which says the force, and I'm just going to find one of those red components. They're the horizontal component. The force will be K Q1 Q2 over the distance separating the charges squared. It's going to be a tight squeeze to put in all the numbers here. I like to approximate K as 9 times 10 to the 9th. Easy to put into the calculator. And as long as all of my charges are put in coulombs and my distance is in meters, then I don't need to worry about putting the units on K. I might set that off with parentheses. And one of my charges is 3 times 10 to the minus 6, that's micro. I'm ignoring the sign, the negative, because I'm just interested in the magnitude at this point. And the other is the fundamental charge of 1.6 times 10 to the minus 19 coulombs. Again, leaving the units off. Now, we have to look at the geometry here to get the distance separating them. I'll draw this in a different color, maybe an orange, and we need to get this distance here, which is the hypotenuse of a triangle formed by 2 and 7. So 2 squared and 7 squared is 53, which makes that length there the square root of 53. I could put that in as a decimal form, but since I'm not really done with the problem yet, I'm just going to put it in as radical 53. And of course that gets squared. So there is the magnitude of an individual force. Those are the ones marked in green. And now what I'm going to do is I'm going to incorporate the cosine of the angle made, and I'm going to mark the angle here also in orange. This is the angle between that horizontal component and the actual force vector, or the red and the green vectors. Now that angle there would be the same angle formed down here with that triangle we just referred to. It's a 2 by 7 triangle. And so if we do a little trig, using 2 and 7, use the inverse tangent function, we'll find that angle there is about 74 degrees. So what I want to do is find that horizontal component, or the adding component, by incorporating the cosine of 74 degrees. Another shortcut you might see occasionally is, instead of actually going to the trouble of getting that angle 74 degrees, you can just use what that cosine of 74 is equal to. That's just the ratio of the adjacent side to the hypotenuse. So you could write 2 over radical 53, and that's the same as cosine of 74. Alright, so that is the value of one of the horizontal components there. And then we would need to double that to get the entire thing. Going to get a little more space here. So an individual force here is about 2.24 times 10 to the minus 17. And because I kept all my units in MKS units, then we can assume those are in newtons. And we're going to double that to get the sum of those two horizontal components, which gives us about 4.48 times 10 to the minus 17 newtons. And that shows the net force due to both the negative and the positive charges A and B as they're indicated. Now, obviously, if we're asked to explicitly name the direction, it's a good idea to do that. With these kinds of problems, it's not always obvious, and so we would just need to include a word, and I think the best word to use here is rightward to express the sum of those two adding components or horizontal components. So there's a good example of a little bit of symmetry and still a little bit of brute force math with the calculator. I'm trying to take a little bit of a shortcut using the symmetry and getting a net force on a charged particle.